state space models. And to start with, we would like to look at this translational mechanical system. As you can see in this system, we have a spring, a damper, and a mass. Also, we apply force F. Now, before we talk about state space model and how we can obtain that model for this system, we would like to just write down the governing equation for this system. So from basic mechanics and free body diagram, we can write down the equation of motion for this system as m, which is the mass, x double dot plus c x dot plus k x equals to f. Okay, so this is the differential equation for this system, and I want to convert this to state space model. Essentially, the state space model gonna represent the same system with a set of first order differential equation. Now, the first thing that we would like to do is that we gotta find out how many state variables we need here. And that's very easy to find out. Literally, you look at the maximum number of derivative of your dependent variable, in this case x, because we have x double dot, it tells me that I'm gonna need actually two state variable. So the next question is that how can we choose the state variables? Well, there are different methods, but the method that I would like to talk about it today is called phase variable method, and it can be used for defining control-oriented systems. And it goes like this. The state variables will be picked to be the dependent variable, in this case x. Let's call it z1, and its derivative z2. Now, because as we just mentioned, we just need two state variable because it's a second derivative of x, we stop here and we're not going to define the third state variable. After defining the state variable, the next step to obtain the state equation is just to obtain the first derivative of your state variable. In the other words, I'm looking for z1 dot as well as z2 dot. Now, just take a look at z1. z1 equals to x. Therefore, z1 dot is x dot. However, x dot is equals to z2, so I can write down here z2. But what about z2 dot? Now, z2 dot, because z2 is equals to x dot, is so z2 dot gonna be x double dot. So in order for me to find out the value of x dot, I'm gonna use this equation right here and solve it for x dot. I'm gonna move everything to the other side with a negative sign and then divide it by m. It's gonna be minus k divided by m x minus c divided by m x dot plus 1 over m times f. Now, in the next step, I'm going to use this equation and replace x with z1 and x dot with z2. So z2 dot would be equals to minus k divided by m z1 minus c divided by m Z2 plus 1 over M. So these are my state equation. The only other things that I need to do is to write it down in the matrix form. So I'm going to do it right here. I'm going to write down the vector of state variable derivatives. It's going to be z1 dot and now z2 dot. Okay, this is equals to this matrix that we call it matrix A multiplied by vector of a state variable, which is going to be z1 and z2 and plus this other vector, we call it b, and it's going to be multiplied by our input, in this case f. Now take a look at this first equation. I'm going to write it down here. In the matrix form, it would be 0 times z1 and 1 times z2 and 0 times f. Now the second equation would be minus k divided by m z1 and minus c divided by m z2 and 1 over m divided by multiplied by f. Okay, so these are the state space equations. In order to have the state space representation, I need to only add the output equation as well. Let us assume that the position x is the output. Then I can write down the output equation y equals to this vector, which is c multiplied by state variable vector z1, z2, and I can type here 1 and 0, which of course this is equals to z1 and equals to x. Okay, so these sets of equation together are state space representation of this spring mass system. Now, let me do one thing. Let me also obtain the transfer function for this system, and then let us go and open Simulink and simulate the response of the transfer function as well as the state space model here, and they're going to be identical. For the transfer function, I'm just going to apply the Laplace transform to this equation, mx double dot cx dot plus kx, and that would be m s square for x double dot plus c s plus k, everything multiplied by Laplace of x, which is uppercase x of s. That's going to be equals to f of s. Now, a transfer function is the Laplace of output divided by input. In this case, x divided by f, and that's going to be equal to 1 over m s square plus c s plus k. Now, let us assume some values for c, k, and m, and then we'll go ahead and simulate this step response of this transfer function as well as these state space model. And essentially, these are identical in terms of like they're modeling the same system. And we're going to see that in Simulink in a second. Meanwhile, let us assume m equals to 1 and c equals to 2, and k equals to, let's say, 5. If you want to make it like the damping a little bit less, let's consider 0.1. Okay, let me open MATLAB and then we can simulate it there so you can see how we can simulate state space models in MATLAB. Gonna take a minute for MATLAB to start working. Okay, MATLAB, let me open Simulink. Okay, so this is our Simulink model. I'm gonna add a bunch of blocks like the scope, um, like this summing junction, um, probably the integrator, and from the continuous, I would like to have the transfer function block, and also I would like to come here under user defined function. I would like to add a MATLAB function as well. And under source, I would like to add the step response. Okay. Okay, so in the first step, let us just simulate the transfer function because that's going to be easier. So it's going to be s squared um, plus 0.1s plus 5. S squared. So here, 0.1 and 5 and s squared. So that's going to be the denominator coefficient. Numerator is 1. And hit apply. Okay. Let me make it a little bit bigger so you can see the transfer function actually. And we can see the step response. Let me simulate it real quick. Okay. Um, Now I would like to just do a little bit of change here under the configuration parameters. I just want to limit the maximum step size. I just want this to be maximum 0.1 second, so the curves looks a bit smoother. Okay. Now, this is the just the transfer function, but we would like to now use the state space model and obtain the same result. For the state space model, let us assume that actually, let me put it here. Let us assume that this signal, if I can write, I would like to write x. Actually, this is d of x, like x dot, and then the signal afterwards gonna be just x because we take the derivative. It's gonna be just x, and this one I'm gonna call it c, uh, and I'm gonna have the scope here as well, and then I'm gonna take one other thing here and another one right here. I'm gonna rotate this, Control R, and I'm gonna take a feedback from X. I'm gonna call this matrix A, and this matrix is gonna be B, uh, and obviously they share the same input. Now, if we take a look at the model that we just developed here, in this model, let me actually pick a different color. This matrix is what we call it A. This matrix is what we call it B. And this guy is C. Considering the value that we use for K, M, and C, matrix A is equals to 0, 1, minus 5, and minus 0.1. Okay, this is A. Let me just define A before I forget it, and then I come back to define the other matrices as well. So this is going to be matrix A. A equals to 0, 1, minus 5, minus 0.1. Then output is A times U. Okay, so this is the output. And let us save this actually. Uh, okay. Now let me define matrix C. We get back here, C is just 1 and 0. So I'm gonna define C is a row matrix, and then the output is C times Y. Okay. Now matrix B, if you take a look here, is 1, 0 and 1 over M. So essentially 1 over M just going to be 1 in this case because M is 1. It's going to be just 0 and 1. What's a column vector? So B using semicolon because that's how we define column vector in MATLAB. Okay, perfect. Let me just simulate this. And as you can see, this is the response from state space model, and this is the response from the transfer function, and these are identical essentially. Both the transfer function way of simulation and state space model essentially have the same result as it should be. One thing I forgot to mention, this integrator is where you got to define your initial condition. And we have two state variables, so I'm going to put 2, 0 here. Now, if you do not update this when you add controller, you would receive an error that says a dimension mismatch. So be careful if it's like third order or more, you're going to update this accordingly with the initial condition of your system. Let's simulate one more time. And yeah, both of them work. And these are the same. Obviously, we can simulate the state space model inside the MATLAB coding as well. And that's going to be something that I'm going to show you in the next video. I guess the only thing that I would like to emphasize that if this diagram is new to you guys, this diagram is literally, if I write it like x dot equals to ax plus bu and y equals to cx. So the MATLAB diagram literally works like this, that you had the integrator, and then this is going to be x signal before the integrator, it's x dot, and then this next block was c, that's going to output y, that is y, and then you had a feedback to the matrix A, and then it goes to this summing junction, and then here is B. This is the output, the input U, and essentially these are like identical thing, you know, either in terms of diagram or like the state space equation representing the same thing. And you can verify that. Just look at this summing junction, UB plus XA equals to X dot, and a BU and AX equals to X dot, so the same thing, and X times C is Y, and as you can see, it's the same thing. Okay, guys, I'm gonna upload more videos about state space models, as well as modern control techniques such as pole placement, also design of integral control, design of observer, and many more interesting topics about model control. So please make sure that you keep checking the channel and stay updated with the latest videos. Thank you so much, and see you guys soon.